Hello folks, welcome to CodeCrucks. In this video, we will discuss the closure properties of regular languages. So before we go to discuss the closure properties of regular language or DFA, let us first understand what do we mean by closure property. So when we take two elements from same set and we perform some operation on those elements, and if we are getting the output, if that output or that results belongs to the same set from which we have taken these two elements, then we can say that that set is closed under that operation. For example, if we choose 4 and 7, which belongs to set of natural numbers, and if I perform addition operation between them, then it results into 11, and 11 is definitely part of set of natural number. So this is one instance. But if this is true for all x and y belongs to this set of natural number n, and if x plus y belongs to n, n is closed under addition operation. Let us consider multiplication. So if we take two element 4 and 7 from capital N, if we multiply it, output is 28. 28 belongs to capital N. But we have tested it for only one instance. We have to make sure that it is true for all the values in n. If we pick up any two random values, and if it is giving us the value which is again part of n, then we can say it's n is closed under multiplication. Let us consider subtraction operation. So 7 minus 4 is 3. So plus 3 is in n. But it doesn't mean that its a set is closed under subtraction operation, because when we do 4 minus 7, then it results into minus 3. And minus 3 is not part of n. So we will say that n is not closed under subtraction operation. So this is not true, and hence n is not closed under subtraction operation. If we consider division operation, maybe 10 by 5 is 2. So that is in n, but from that we cannot claim that division is closed. 4 by 7 would be 0.57. It is a fractional number, so it is not part of n, and hence we can say that set n is not closed under division operation. Now this set from which we are deriving two different entities to perform various operations could be different. For example, now we are taking it from capital R, that is the set of real number. It contains all the real numbers, negative, positive, everything. So if you perform addition operation, it is definitely in R. So R is closed under addition. R is also closed under multiplication. And 4 minus 7 is minus 3. So minus 3 also belongs to capital R, because R is set of real numbers, which also includes negative and positive. So we will say that R is closed under subtraction operation. And similarly, 4 by 7 is 0.57, and we know that it also belongs to capital R. So division is R is also closed under division. So from this we can conclude that set n is closed under addition and multiplication, but it is not closed for subtraction and division operation, whereas set R is closed under all these discussed arithmetic operations. Now we will extend our understanding for regular language. So formally we can define that closure properties of regular languages are described as specific operations on regular language that are ensured to create regular language. So for example, we are given two regular language and we perform some operation on those two regular languages, and if generated language is also regular, then we can say its languages are having a closure property for that particular operation. So regular languages are closed under union, intersection, difference and complement, and we are going to discuss all of them one by one. So let's start how to do that. So first we need to create a combined machine. Assume that M1 and M2 are two DFA which are producing language L of M1 and L of M2. How to construct combined machine, that we have already discussed in previous videos. A link of that video is given in description box, and the algorithm we have already discussed. So what we have to do is, first we have to add the S0 Q0 to M3, and then we have to iterate through a loop, that for every state Si, Sj in M3 we have to do this. So right now we have only one state S0 Q0, so that will pick up and will expand it. So how to expand? We have to find out delta C transitions for Si comma Sj, Si comma Qj. So if it is not expanded, then we will do this. So for every alphabet ak in the sigma, we will find this transition. Okay, we have to add the transition delta 1 Si comma ak and delta 2 Qj comma ak. So we are reading alphabet ak from Si and we are reading same alphabet ak from Qj state, and whatever combination we are getting, that we have to add to M3. And this process we have to repeat until all the states of M3 are expanded. So algorithm is explained in detail with explanation in my previous videos. If you have any difficulty in understanding this, I suggest to watch those videos. Okay, we can derive machines M3, M4 and M5 from MC, from this combined machine, by selecting certain states, such that if we want to create machine for union, then the language generated by machine M3 is equivalent to L of M1 union L of M2. So we have one machine M1, we have another machine M2. The language produced by M1 is L of M1, language produced by machine M2 is L of M2. Now we have to find the combined machine which will produce the union of the language generated by M1 and M2. So how we can do that? So now it's quite simple. Once we have a combined machine, we just have to adjust the final states. So for union operation, the F3, that is the set of final states in machine M3, is given as Si comma Qj, such that Si belongs to F1, that is Si must be final state in machine M1, or Qj belongs to F2, that is Qj must be final state in machine M2. So if one of the state in combined machine is in final state of the original machine, then we have to consider it as a final state in the combined machine. So that combined machine will become equivalent representation for the union operation. So if we do this kind of setting, then combined machine will act as a union of M1 and M2. To construct the machine for intersection, so in that case, the OR is replaced by AND. It means Si and Qj both must be final state. Only those states we have to mark as a final state in combined machine MC, and we will call that machine as a M4. And to find the difference between two languages, L of M1 minus L of M2, we will make sure that only those states in combined machine MC will be marked as a final state in which Si is final state but Qj is not final state. And this machine we will call as a M5, and which is equivalent for difference of the language, M1 minus M2 machine. Let us try to understand it through the example. So first we have a M1 is given like this, M2 is also given. Now we will construct the combined machine. So by algorithm we know that the first state to be added into combined machine is the initial state Q0, S0, Q0. So S0 is the initial state of M1, Q0 is the initial state of M2. So in M1 initial state is Q1, in M2 initial state is Q4. So first we have to add Q1, Q4 to MC. So MC is right now a partial machine which contains only one state. Now we have to expand these states in MC, and to expand that we have to apply the delta transitions on Q1 and Q4 for all the possible input alphabets. Right now M1 and M2 contains only two input alphabets, A and B. So we have to apply delta 1 transition on Q1 for input A and delta 2 transition on Q4 for input A, and same process we have to repeat for the input B as well, and that will give us the combined state. So delta 3 Q1 comma Q4 on input A is given by breaking it into two parts. So we have to apply delta 1 transition on Q1 for input A and delta 2 transition on Q4 on input A, because Q1 is coming from machine M1 and Q4 is coming from machine M2. So that's why we have to apply the delta 1, delta 2 transitions, and that will give us Q2, Q4. So this is the new state, and that we need to add into the partially constructed machine MC. Same process we will repeat for input B now. So when we apply input B from Q1 Q4 state, we are getting a new state which is Q1 Q5. So as of now we have a 3 states in combined machine. First one is the initial state which is Q1 Q4, then Q2 Q4 and Q1 Q5. And normally we can simulate these things with the help of Q. So Q1 Q4 was the initially generated state, so it is at the first position. Then Q2 Q4 we are inserting into Q, and Q1 Q5 we are inserting into this Q. Now Q1 Q4 is expanded, it's processed. So we are showing it into green color, we are showing it into gray color, and green color states are yet to be expanded. So one by one states we will pick up from the Q and we will expand it. So let us expand let us expand Q2 Q4 state. So we will read A from Q2 Q4 and we will find out what is the output, and then we will expand it for input B. So when we apply the delta 3 transitions for input A on Q2 Q4, we are getting Q2 Q4 itself as an output. So there will be a self loop, right? When we read alphabet A from Q2 Q4, we will remain onto the same state. So we have to make a self loop in that case. And when we read B, it is generating a new state which is Q3 Q5. So Q3 Q5 we need to insert into the Q. So now our Q looks like this. Q2 Q4 is processed. Now we will pick up Q1 Q5 and we will expand it. So we will apply the delta transitions for input A and B alphabet. When we apply it for A, it generates Q2 Q5, which is a new state. So we need to add it into the Q. And when we apply B transition, it produces Q1 Q4, which is already there. That state is already there into the Q. So we only have to insert Q2 Q5 into the Q. And Q1 Q4, Q2 Q4 and Q1 Q5 states are already expanded. Now we will expand Q3 Q5 state. Okay? That is Q3 Q5. So again apply delta transitions for input A, which gives us Q2 Q5, and apply the delta transition for input B, which gives us Q1 Q5. If states are same, we don't have to push it into the Q. If it is a new, then we have to insert. So there is no new state. Q2 Q5 is already in Q. Q1 Q5 is already in Q. So no states are added into the Q. Last state we have to process now because it is not expanded. So we need to expand Q2 Q5. So let us read A from that. It leads us into the same state Q2 Q5. So there will be a self loop. And when we read B, it generates Q3 Q4, which is not in Q. It means it is newly generated state. So we need to add it into the Q. And we will expand that state Q3 Q4. Let us find transition on A, that is Q2 Q4. That state is already in Q. So we don't have to add anything. And then we find transition on B, it gives Q1 Q4. That state is also in Q. That means all states in Q are expanded. So all cells are now gray. So here we have to stop. And now we will build the combined machine. So this will be the combined machine. Right? From Q1 Q4, if we read A, we are moving to Q2 Q4. And if we read B, we are moving to Q1 Q5 and so on. So this is the combined machine. From this combined machine, now we have to construct the machine which generates union, intersection and the difference. So for union we have already discussed. See, in original machine M1, Q3 was the final state, and in machine M2, Q4 was the final state. For generating the equivalent DFA for union, we have to set all those states in MC as a final state in which either SI is the final state or QJ is the final state. So if we consider Q1 Q4, then it will be marked as a final state because Q4 is the final state. If we consider Q2 Q4, it will be marked as a final state because Q4 is final state. Next is a Q3 Q5. So Q3 is a final state, so we will mark that as well as a final state. Next is a Q1 Q5. So in neither Q1 nor Q5 is final, so that we will not mark as a final. Q2 Q5 we will not mark as a final because neither Q2 nor Q5 are final in the original DFAs. and in Q3, Q4 is final state in machine 2, so that will be marked as a final state. So union will have total 4 final states. So this is the DFA which will produce the union language of machine M1 and M2. So once we have combined machine, it's not difficult. Let us consider the intersection. So to construct the equivalent machine which computes the intersection of languages produced by M1 and M2, we have to mark only those states in MC as a final state in which SI is also final state and QJ is also final state. So if we look at that, then Q3 is final state in F1, Q4 is final state in F2. So only that state will be marked as a final state which is Q3 comma Q4. So this is the final state, or this is the final DFA for intersection. So this DFA will compute the language which is equivalent to L of M1 intersection L of M2. Let us find the DFA equivalent to difference. So for that we have to mark only those states in MC as a final states in which SI is final state in M1, but QJ should not be final state. Fine. So if we talk about all the states, then Q3, Q5 and Q3, Q4. In this two, SI, that is the first state, is a final state, but second state should not be the final state, right? Because QJ must not be in F2. So in Q3, Q5 that condition is satisfied because Q5 is not final state in M2, but in Q3, Q4 it does not satisfy because Q4 is the final state in machine M2. So there will be only one final state which is Q3, Q5. So this is equivalent DFA for computing difference language, that is L of M1 minus L of M2. And to compute L of M2 minus L of M1, we have to just alter in that way. Okay, we have to select the final states according to that. So in that case, Q4, we have to compute the machine and we have to check that Q4, Q3 should not be selected as a final state. It should be Q4, Q2 is a valid state. Q4, Q1 is valid final state. Okay, so there will be 2 final states if we compute L of M2 minus L of M1. The last one is a complementation operation. So that is very straightforward and very trivial. How we can achieve it? So for M1, some machine M1, to prove the closure property of complementation, we should find out another machine M2 such that L of M2 is the same as L of M1 complement. To do that, we have to do very simple changes, like we have to make every final state in M1 to non-final state in M2, and we have to make every non-final state in M1 to final states in the M2. So we just have to change the role of every state and we will get the complemented DFA. So if M1 is Q sigma delta Q0 F, then M2 would be Q sigma delta Q0 and Q minus F. So we are simply taking complement of the final states. Everything will remain as it is. Assume that we have one DFA like this. If we look at the DFA carefully, then it will accept all the strings in which number of B's are even. If we read first B, it is going to Q1, which is not final state. When we read second B, we are in Q0, which is final state. So 2 B's are accepted, 0 B's are accepted, 4 B's are accepted, and so on. And it has 2 states Q0, Q1. So the language accepted by this machine M is all the strings W such that W belongs to A, B whole star and number of B in W are even. To compute the complement DFA of this, we just have to change the role of Q0 and Q1. So Q0 will become initial state, Q1 will become the final state. And if we look at this, then 1B is accepted, 2B is not, 3B accepted, 4B not, 5B accepted, 6B not. So this is DFA which generate the language L of M such that it is set of all the strings W where W belongs to AB star and number of B in the W are always odd. So this is exactly complement language of machine M. So we can say that regular language is closed under union, intersection, difference, and complementation. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment, and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.